Hey, it's Weinstein, and today we're looking at the fastest punch in the animal kingdom and what it's teaching engineers. There's an animal that punches at the speed of a bullet, 23 meters per second, a blow powerful enough to shatter crab shells and crack open mollusk shells. And now the strange part. Its own fist comes out completely intact, not a scratch. And this happens thousands of times over a lifetime. Any hammer we make would have fallen apart long ago. It just keeps hitting. This fighter is called the mantis shrimp, a small marine creature brightly colored as if painted by hand. To look at it, a pretty harmless shrimp. In reality, the owner of the fastest punch in the animal kingdom and possibly the toughest hammer on the planet. Its fist is the envy of engineers. And the headache of materials scientists. It hunts simply and terrifyingly. It spots a crab or snail, creeps close, and strikes with its front limb at monstrous speed. A shell you couldn't crack with your hands shatters in one strike. Shells as hard as rock split apart. It literally punches its dinner open and does this day after day for its entire life. The blow is so fast that the water around it can't get out of the way in time. Tiny cavitation bubbles form and then collapse instantly, releasing another burst of energy. The result is a double blow. First the fist, then the collapsing water. The prey gets hit twice. Nature was generous this weapon works, even if it misses. And here's the puzzle that materials scientists have been wrestling with for decades. Hit anything with that kind of force against a hard surface, and your tool will suffer. Metal dents, ceramic cracks, glass shatters. You can't fool physics, an impact punishes both sides, yet the mantis shrimp's fist comes out unharmed. Thousands of strikes, not a single crack all the way through. How? Think about what this actually means. Normally, a material is either hard but brittle like ceramic or glass, or tough but soft like rubber. Hard hits hard but chips. Soft doesn't chip, but can't hit hard either. Yet, the mantis shrimp's fist manages to be as hard as rock and still almost never break. It defeats the usual trade-off. Its weapon is called the dactyl club. It's the thickened end of the front limb, the hammer itself. Small, just a couple of centimeters. But that's what smashes shells and casings. From the outside, nothing special, dense, smooth, hard. All the magic is hidden inside in the microscopic architecture of this hammer, and scientists managed to crack it open. In 2012, David Weaver and colleagues published a detailed analysis of this club in the journal Science. They described it in the paper as a formidable, damage-tolerant biological hammer. The scientists sliced, imaged, and examined it layer by layer. Inside, they found an architecture that any engineer would envy. What they saw changed the way we think about impact-resistant materials. It turned out, the club isn't a solid chunk of uniform hard material. It's a complex, multi-layered structure of several distinct zones, each with its own job. There's a hard impact surface that takes the blow, a zone beneath it that absorbs the energy, and a lateral region that keeps the club from flying apart under load. A genuine engineering ensemble packed into a couple of centimeters? Let's start with the impact surface, the part that meets the shell. It's made of a very hard mineral called hydroxyapatite. That's the same material our tooth enamel is made of. Hard, dense, perfect for smashing, but hardness alone is exactly the recipe for brittleness. Hard things usually chip, so there has to be something behind it. And there is. Hidden beneath the hard outer shell is the main secret, a special fiber arrangement. The fibers aren't laid randomly, and they aren't laid in flat parallel layers either. They're arranged in layers, but each successive layer is rotated by a small angle relative to the one before. Layer by layer, turn by turn, the fibers wind into a continuous spiral. And this structure has a name. It's called the Bouligand structure. Picture a stack of sheets, each printed with parallel lines. You lay one sheet, then place the next, rotate it slightly, then another, rotate it a little more, and so on, hundreds of times. The fiber direction slowly rotates deeper into the material, like a spiral staircase. That's exactly how the mantis shrimp's fist is built, and it changes everything. A fair question arises, what's wrong with ordinary straight layers all pointing the same way? The problem is that this kind of material has a weak direction. Fibers carry load along themselves, but it's easy to split them apart. A crack only needs to find that convenient corridor and it races straight through between the layers like a knife through butter. Straight layering essentially gives the crack a roadmap. Now, the spiral. A crack starts running along the fibers, but a little deeper, the fibers are already rotated. The crack has to turn. A little deeper, still another turn. It can't go straight. To keep moving, it has to constantly change direction, twisting along with the layers. There is simply no straight path through. only a long, winding spiral road. And here's the trick. Every turn costs energy. As the crack spirals, it burns through the impact energy and it spreads across a huge volume of material. Instead of one catastrophic fracture, the energy fans outward, smearing across the entire club. The impact doesn't punch through the material, it sinks into it. It dissolves, like a wave into sand. And this is a fundamentally different approach from simply making a material harder. Hardening tries to resist an impact by brute force. The harder, the better. But that strategy has a limit, beyond which the material just shatters. Dissipation means absorbing a blow and spreading its energy through yourself. Not resisting, but absorbing and redistributing. A completely different philosophy. A simple analogy. Punch a concrete wall, it hurts, and the wall might crack. Punch a thick pillow, it accepts the blow, dents, disperses in a wave, and nobody gets hurt. The spiral structure works like that pillow, but inside a hard material. It accepts the impact and spreads it while staying hard on the outside. The best of both worlds. But there's more. The club has a lateral zone, built on a different principle. Herringbone. The fibers there are laid in a cross-grained zigzag pattern like herringbone hardwood flooring. The job of this zone is to keep the club from splitting sideways. Under powerful compression, a material tries to expand outward and burst apart. The herringbone wraps around it, suppressing those tensile stresses. This sounds paradoxical. You're compressing something and it tears. But that's exactly what happens. Squeeze a rubber eraser and it flattens, spreading sideways. In a hard material, that spreading creates tensile stress at the sides and brittle things fail precisely in tension. The herringbone wraps the club like a bandage, keeping it from spreading apart. A hoop around a barrel. The full picture comes together now. A hard impact surface to smash. The Bouligand spiral beneath it to confuse and disperse the crack. The herringbone on the sides to keep the club from splitting under compression. Each zone does its own job, and together they give you a hammer that hits like a bullet and stays in one piece. Not one clever material, an entire architecture. And here's the key conclusion. The club's toughness isn't in some wonder material. Hydroxyapatite is also in our teeth. Chitin is in every shell. Ordinary materials, everything comes down to how they're arranged. In the spiral, in the rotation angles, in the alternation of zones, the secret isn't what it's made of, it's how it's built. Architecture matters more than composition. Having cracked the mechanism, engineers got to work. The idea is simple. If a spiral arrangement saves the mantis shrimp's fist, let's arrange our composites the same way. Carbon fiber, fiberglass, ceramics, the materials we use to make lightweight, strong parts. Not change the material, change the order of layers. Lay them in a spiral, the way nature did. By 2021, enough research had accumulated that the journal Matter published a full review. How the Dactyl Club's principle is being applied in impact-resistant materials. Scientists tested spiral layups, tuned the rotation angles between layers, hit samples, and recorded what held up. The answer? It works. Spiral layup genuinely improves impact resistance. And a curious detail emerged. The rotation angle between layers matters enormously. Too large and the layers don't work together effectively. Too small, and the spiral is barely different from a straight layup. There's a sweet spot where the crack gets most thoroughly confused and damage spreads most widely across the area. Nature found that angle long ago. Engineers are now dialing it in for their specific applications. The test results are striking. Hit a standard plate, the crack runs straight through and a piece breaks off. Hit a spiral plate, the crack twists, splits, fans outward, and stalls. The material at the impact point is dented, but not punctured. The damage smears across a large area instead of leaving one clean hole all the way through. Exactly what the Mantis Shrimps Club does. And in 2025, the story took an unexpected turn. A team led by Horacio Espinoza at Northwestern University found an effect hidden in the Bouligand structure that nobody had anticipated. It turned out the spiral doesn't just confuse cracks, it also acts as a filter for shockwaves. And that's a whole different level. Let me explain. When an impact happens, it doesn't just send a crack through a material. A wave also runs through it, a vibration, a tremor that travels deep inside and beyond into the body. Think of it as a very powerful sound. And these waves can cause damage even where there's no visible crack. They shake and destroy everything they pass through. Invisible injury. And here's what scientists found. The Bouligand spiral structure physically blocks waves of certain frequencies. This is called a phononic band gap. In plain terms, for some vibrations, the material becomes a solid wall those waves simply cannot propagate through it. They're not gradually dampened, they don't get through at all. The door is shut. Imagine noise-canceling headphones, but built into the material itself. Some frequencies pass, others don't, the structure filters them out. The spiral inside the club works like exactly that kind of filter. The most dangerous high-frequency vibrations from the impact simply aren't allowed to travel deep into the limb. The mantis shrimp strikes and its own body doesn't shake from the recoil. Brilliant. So it turns out, the same spiral provides protection in two entirely different ways. First, it confuses and disperses cracks' mechanical protection. Second, it filters shockwaves' wave protection. Two different threats, one solution. Nature didn't build two separate mechanisms, it found a structure that handles both. That's an extraordinary economy of engineering thought. And for us, this is enormous news. In many impacts, it's the waves that cause the real damage, not the visible cracks. We're used to thinking, if the surface didn't crack, everything is fine. But that's not true. The wave travels inside and does its damage where we can't see it. And now we have a clue about how to stop it. And here's where this becomes critically important. Helmets. Hard hats, cycling helmets, sports helmets, we assume, put it on and your head is protected, the helmet didn't crack, so everything is fine. But ordinary helmets handle the wave badly. The blow lands outside, the helmet stays intact, and the concussion still reaches the brain. A hard shell doesn't protect against what propagates straight through it. And this isn't an abstract problem. In America, this issue has long reached far beyond sports. It concerns chronic traumatic encephalopathy, CTE, a degenerative brain disease found in former American football players. Years of collisions on the field, and the brain pays the bill. Depression, memory loss, dementia, and sometimes a tragic end. The price of the sport turned out to be far higher than anyone thought. The most insidious part is that the big knockouts aren't the real culprit. The most damage comes from ordinary, routine collisions, the ones after which a player gets up and keeps running. Hundreds of them per season. Each time, the brain shakes inside the skull from the shockwave, each time, microscopic damage, and the helmet comes out without a scratch. It protected the skull, but not the brain. And here's the helmet's fundamental flaw. It handles the gross mechanics brilliantly. It keeps the skull from being fractured, distributes the direct blow, but the vibration energy still passes right through it and reaches the brain. The shell protects against the crack, but not against the tremor. That is ordinary helmet's blind spot. And that's exactly where the discovery of phononic bandgaps strikes. Imagine a helmet with layers arranged in a Bouligand spiral. It doesn't just absorb the blow, it cuts off the dangerous frequencies, preventing the wave from reaching the head. It handles both the crack and the vibration at once. Not a cure-all, of course, but exactly the kind of protection that helmets have always been missing. A tiny crustacean is pointing the way to protecting athletes' brains. It sounds incredible, but that's exactly what's happening. Back to everyday life. Smartphone cases. Drop your phone and all hope rests on the case. An ordinary case just cushions the blow as best it can. A case with a spiral structure would disperse the impact energy across its entire surface and prevent it from reaching the fragile screen. The same principle that saves the mantis shrimp's fist. Only now it's saving your phone. Next, armor. Bulletproof vests, armored panels, vehicle protection. Same task, take a tremendous impact and stop it from going through. Classic armor relies on hardness, but cracks after several hits. A spiral layup spreads the damage and lets the panel hold up hit after hit, just like the club that hammers thousands of times and never breaks. And finally, aviation and aerospace. There, composite panels constantly take hits. Hail, runway debris, microparticles, assembly impacts. The surface looks fine, but inside, there's delamination invisible to the eye and potentially catastrophic. Spiral fiber layup makes such panels far more resilient. Light, weight, plus impact resistance, the dream of every aerospace engineer. Stop and take in the scope. The same spiral works in the fist of a tiny marine crustacean, in a smartphone case, in a sports helmet, in an armor panel, and in an aircraft fuselage. From hunting crabs to protecting the brain and flying to space, one clever layer arrangement and brittle becomes tough. Nature found a universal trick. But let's be honest, the mantis shrimp is an inspiration and proof that this approach works, not a finished blueprint for a helmet. Reproducing its multi-zone architecture in a cheap, mass-produced product is a serious challenge. A lab sample and a production run are different universes. Nature supplied the principle and proved the payoff. Turning it into something mass-produced is the engineer's job, and that work is underway. And the fine-tuning is real. The spiral layup has to be precisely calibrated for the material, angle, thickness, and type of impact. It also makes manufacturing more complex and expensive. A helmet still has to be light, comfortable, and affordable. Scientists and engineers are working all of this out right now. Progress is real, but the road from a beautiful paper to a helmet on the field is still being traveled, step by step, and that's completely fine. The mantis shrimp was solving its own problem, cracking shells without breaking its own fist, not protecting a football player's brain. Our job is to spot the key principle in its hammer and adapt it to our own needs. The idea of dispersing a blow through a spiral turned out to be invaluable. The fine details get adjusted by engineers for each specific application. So what do we really take from the mantis shrimp? Not the literal fist. We took the structural idea, lay the layers in a spiral so the crack has to wind endlessly and dangerous waves get blocked. That idea is now being built into composites, helmets, armor, and phone cases. The principle from a tiny crustacean's claw has migrated into protecting people and machines. A small fighter, a big clue. So it turns out, an unassuming little crustacean proved to be a brilliant materials scientist. It solves the problem we're still wrestling with how to hit with tremendous force and not break yourself, and it solves it elegantly through fiber arrangement alone. And it's been doing this for millions of years, long before the first helmet was ever made. Nature was ahead, once again, right there on a coral reef. Put it all together. The mantis shrimp hits at bullet speed thousands of times and never breaks because inside its fist, fibers are arranged in a spiral that confuses cracks and filters shockwaves, while a herringbone on the sides keeps it from splitting apart. We cracked that trick, and now we're learning to make helmets, armor, and cases that survive an impact. Protection borrowed from a tiny crustacean. And once again, the thing that decides everything isn't visible to the naked eye. The fate of the entire structure depends on the rotation angle between layers just a few degrees. Get it wrong, and the crack goes straight through. Get it right, and the crack bogs down. We're used to thinking what matters is big and obvious, but here, an outcome is decided by a microscopic rotation. Enormous toughness from the tiniest detail. And one more thought worth carrying away. The most dangerous damage is often invisible. The helmet is intact, but the brain was injured. The panel is intact, but there's delamination inside. We judge damage by appearances and deceive ourselves. The mantis shrimp understood this before we did. It protects not only against the crack you can see, but against the wave you can't. We should learn to do the same. Here's the thought to leave with. We're used to defending ourselves through force. Harder, thicker, stronger. The mantis shrimp defends itself through intelligence, it doesn't resist the blow, it pulls it apart until it dissolves. Maybe we too should less often meet impacts head-on, and more often learn to disperse them. Sometimes the best way to survive isn't to face a blow with a wall, it's to make sure the blow can't find a straight path through. So next time you see a photo of that brightly colored mantis shrimp, don't scroll past. This little creature owns something engineers dream of: the ability to hit like a bullet and come out whole. And the helmet that one day saves someone's brain, or the phone case that survives a drop, may carry the secret of its tiny fist. Nature figured all of this out long ago. Our job is simply to look and ask, why does that work? Thanks for watching. You're definitely a little smarter now, and you know one more story about how humans borrow their best ideas from nature.